Philosophy. Why are we doing this? Global demand for energy is increasing rapidly. Well, we know this. Fossil fuels are a significant CO2 contributor. So this is the big thing here. It's estimated fossil fuel-based and domestic space heating single-family detached dwellings contributes to 43% of greenhouse gas emissions in the Lower Mainland. This is why they're pulling triggers left, right, and center. We can't say it's cars. It's not cars. The major part of it, and this is the lower mainland. So you're going to have some factories, some things that produce, but the biggest producer, single producer, is single-family dwellings. So that's what they're hitting us up with. So why a heat pump? Greenhouse gas intensity of a heat pump is significantly less than all other forms of heating. So if you look at your step code houses, obviously you're going to use less energy as you get closer to a step 5 house. But if you look at the electrical energy, if you're straight electric resistance right here, there you go. That's your greenhouse gas intensity. Heat pumps are down here. Of course, gas is up here. Hybrid solutions are here. So this is really what's driving this whole requirement. They want to get our greenhouse gas. It's not about using electricity, it's about getting rid of greenhouse gas. End of story. So how do we do that? Do we do that with hybrid heat pumps? Well, City of Vancouver says no. I want 100% electric. 100% electric space heating and domestic water heating. End of story. Is everybody else going to follow suit? I believe so. I would say there's probably a lot more retrofits that go on than new construction. Everybody agrees with that, I'm assuming. For the amount of heat pumps there's a potential to go in, you can only do so many new construction compared to retrofits. Furnaces are breaking all the time. So the first thing you do, the first thing they would want us to do is say, look, ma'am, what you really want to do is upgrade your insulation, do draft proofing, doors and windows, get a certified energy auditor advisor to do a report and tell you what you should do. And in that will be heat pumps. So that's the first step, honestly. You don't want to have a crappy house and just throw a heat pump in and waste all that energy. First step is always the envelope. So why a heat pump? Operational costs? Okay, so Fortis BC, October 2021. Using an HSPF of 9.2, which is not a bad heat pump, but it actually falls below the HSPF that's required for all of the rebates now. So there you go, there's your cost. That's based in October 2021. If this is part of the discussion, fossil fuel, natural gas versus electric heating, it's easy to say, electric heat pump's gonna cost you a lot of money. You're gonna be paying through the nose. But are you? As the cost of natural gas goes up, and if it's not the actual cost of the gas, is it the carbon tax that drives it up? I believe that's the way it's gonna go. The gun is to the head of everybody down the line, starting, believe it or not, with Trudeau, from the feds to the provincial to the cities. They're driving this, and I think at the end of the day, they will drive up natural gas prices and just make it impossible to use natural gas. So put a heat pump in, hey, you get cooling out of it. That's not such a bad thing. What's wrong with that? More airflow can be a problem. Most heat pumps have a lot more airflow. That's not necessarily a bad thing. It's going to possibly do a better job of air filtration. Okay, how does a heat pump work? Warm goes to cold. Same as the warmth in your house is going to migrate outdoors. Warm goes to cold, that's all we got to remember. A heat pump is a device that heats from a lower temperature to a high temperature with little help from boiling refrigerants and some electrical energy. Refrigerants, they boil off, they vaporize at some majorly negative temperatures. Controlling the boiling point or vaporization rate of refrigerant through pressure is how we can absorb heat. You've seen these refrigerants before. These are very common. But R22, as we all know, is part of the past. Do we all know this? Anybody working with the refrigerants should have ODS certification. That's common knowledge. The basic parts of a refrigeration system, starting with the evaporator, moving on to the compressor, condenser, Metering device, also known as expansion valve, thermal expansion valve, whatever you want to call it. Cycle begins here. Okay, we got an outdoor unit. We got an indoor unit. So if this is our heat exchanger in our outdoor unit, and this is our heat exchanger in our indoor unit, if we start from here, low pressure, low temperature liquid. Moving this way to our outdoor unit. Let's turn a fan on in our outdoor unit, and our refrigerant wants to boil. There's heat outside, but remember, what was our boiling point of our refrigerants? Like minus 45. So it can be pretty bloody cold out. You pass that air past this coil, it's going to boil that refrigerant. Changes states, and it absorbs a whole heck of a pile of heat right here. In fact, now we've taken liquid and we've turned it into vapor, low pressure, medium temperature vapor. In comes the electrical input part of the deal. Let's run this compressor and see if we can take that vaporized energy and squish even more out of it. Now we got ourselves some high pressure, high temperature gas. What do we do with that? Let's send that indoors, and let's run through another heat exchanger, the indoor unit. Turn a fan on in there and see if we can pull that energy out of there. What you're left with is high pressure, medium temperature gas, or vapor. Hit the expansion valve, and we simply take the pressure off, let it expand, it cools again, turns back into a liquid, and the whole cycle starts again. Okay, so then you all will know that a reversible heat pump or air conditioner simply employs the use of a three-way valve, a reversing valve. Simple. We take our evaporator, where we had the liquid refrigerant, and we run it through the three-way, the reversing valve, off to the compressor, into the indoor unit. This is heating mode. This is what we just looked at. We're talking about heat pumps, so we're kind of starting with heating pump. So what's going to happen here in the reversing valve, we just simply take our condenser from this side and we move it to this side. Simply do that by reversing the flow. Now the flow of refrigerant is the other direction. Pretty simple device, which is why there's not a big price difference in a heat pump versus an air conditioner. Lack of certification. We've worked for a long time to try to get the certified heating technologist, which would be a heating ticket to work residentially. We have that on standby still. It's in the association. We never got it into government where they mandated that you had it. That's where it got roadblocked. So we don't have a certified heating technologist. It's ready, and now they're looking at it again. Hey, that wasn't a bad idea you had. So maybe it gets through, maybe it doesn't. In the meantime, we have to deal with what we have as far as our skill level. Really, as far as I can see, TECA is the only one that really teaches heating, if you will. Sure, you could get a sheet metal ticket. You can get plumbing tickets, refrigeration, but the overall package of heating, what do you have? So there are heat pumps. Basically, you have air-to-air heat pumps, air-to-water heat pumps, water-to-water, water-to-air, water-to-water heat pumps. Air source, heat pumps that absorb low-temperature heat from outside air. Water source, well, you take it from either the earth or water. That's more or less your geo-exchange. We're here to blab about air-to-air right now. We know that there's ducted central style units. We know there's mini split, there's ducted and ducted, ductless and ducted mini splits, multi-zone, horizontal concealed versions. Your typical, we know how heat pumps work. We don't need to talk about that. What we do need refreshers on sometime, you know, this is very common setup really in North America, but certainly around the lower mainland. So, and particularly in retrofits, you're going to go through a lot of these rascals, these air handlers, central air handlers. So it's got to be big enough. You got to analyze the ductwork. That's where things fall apart. In central air handlers, that's where things are falling apart. Certainly back in the 80s, your gas, CFMs per 1,000 BTU were way down there in the 80s. Then we started getting the high efficiency stuff, and we started moving a lot more air. And now we're talking heat pumps, air or geosource, whatever the source is. You're moving a lot more air. So when we think about retrofits, wait a stinking minute. We're doing this here now, but we're replacing the 1980 gas-fired furnace. We better look at this pretty closely. We got to look at the ductwork because we were moving a lot less air per BTU back then. So the good part about this is everybody had a 80,000 or 100,000 BTU furnace in the truck, so that's what they actually put in. The heat loss and everything else, most furnaces that I see are basically twice the size they need to be. So if anybody did even a rule of thumb bit of homework putting in that 1980 furnace, they had ductwork to match the output of that furnace. It's fairly large ductwork, hopefully. And if it's lasted since the 80s, it's probably not doing too bad anyway, as far as the ductwork sizing went originally. So when we roll in with a heat pump and now we got to do a proper analysis of everything, you probably find that the furnace was oversized and the ductwork might have been oversized anyway for the actual heat loss of the building because nobody really did the work. So what happens, if we start trying to cram more air, if that ductwork is indeed too small, if we have all the same insulation, if we have the 1980s house and we're trying to heat that with a 5-ton heat pump, now we're trying to move a lot of air, obviously. And what happens with that increased volume is increased friction, as you know, increases static pressure. And so doubling the volume of static pressure increases pressure drop by 4 times. So 20% only increase in volume increases static pressure drop by 44%. So it's serious business. Absolutely got to look at it. We all know that you can check static of equipment both before and after you replaced it and make sure that that thing, if it's rated to move 1200 CFM, you check the static rating that's required to move 1200 CFM from the documentation of the heat pump, you're going to find that, okay, we're moving enough air. If your static is right, your temperatures are right, now you're moving enough air. So you got to check these things. You can't just do it and hope for the best. Some of the fittings might be all goofy and you never know what might have gone on. So if we're all electric now, that means this is like here, we've got electric strip. And there's the refrigerant coil there. That's your air handler. That's your central air handler. So if we're going to measure static, this is where we're going to measure in this case. If you wanted, your filters, they have static drop depending on the size configuration. Everything has a bit of static drop. Of course, you could measure across any of this stuff, but this is really what we want to know. We want to prove that we're moving enough air. We got to make sure the static's right. Simple as that. If you had a dual fuel unit, then the rating of the heat pump itself, so the fan, the furnace, if it's a furnace, you're probably going to have the coil plunked on top there. Now, the furnace doesn't necessarily know what coil that is, so the documentation of the furnace and the static pressure it's going to develop is going to say, yeah, I'm 1200 CFM, this amount of static. So if your coil is plunked on top there, you got to make sure you don't measure the static there because it's the prediction of the static resistance of that coil that you plunked on top is not part of the data that comes with this unit. It's easy if you're going all electric. If you don't do the dual fuel thing, it's pretty easy to just measure either side. You got the electric strip in there, that may not become part of it. It's not a serious issue either way. Single zone heat pumps, mini splits. So yeah, I assumed, mostly, if you got electric baseboard, I want the heat pump, I want the cooling. A lot of people just the cooling drives this, let alone the rebates, but the cooling seemed after last year seems to be a big deal and everybody wants it however you get it. So if you've got a radiant floor, if you have a non-ducted system, that's where I see these go in mostly. The thing about ductless, if you look at the performance of them, or if you're into the rebates, and which is another conversation which we might have time for, you look at the rebates, everybody loves them. The government loves them because They're not leaving it up to you to figure out ductwork with air handles central. Is it done right? Is it static right? Oh, the distribution, is it working properly? If you just go ahead and take a outdoor unit and put in a wall mount unit, what's to go wrong? It's all designed in a factory. So the performances are basically higher and they stay that way. So I think you'll find it's the government feels it's a more efficient solution, and it's easier to get rebates based in that. Now, I think that North America is not necessarily ready for them all over the place. If you were building a new house, would you put wall mount units in? I don't know. I'm not so. I think I'd look at other ways to do it. Retrofit, if I had to, I guess I'd do it. Multizone, well, you guys all know this stuff, right? Now that's even more handy. You can do what you're saying, right? You got your air handler there, you got a few of these back or forth, you got VRF, or you got multi-zone where you've got to pipe all the refrigerant back to the unit. That simplifies things quite a bit. It's not as popular, there's a little bit more going on there, but it's an efficient way to go. So as soon as you start to multi-zone now, you can, well, I'm going to turn the room down, the heat down in this room, and I'll have it up over here. It's balanced, you're keeping more people happy. At the end of the day, it's, these are more likely to be better engineered. A lot of these things, so now maybe it is my new house now. Oh, where are you going to put, I want that, all that zoning, but I don't want to zone ductwork and all that. You got units, well, conceal these things, great. So they're a pretty common application now, I think, but you got to be careful. So you got two different applications. Like, nothing wrong with doing this. Sure, that's what you see in a hotel all the time, but you can make that look good. But look at the amount of ductwork on it. How about none? Or maybe you put a few feet on there and it's out. You're done with the static. So be careful. Don't just get a horizontal unit. Oh, I like the thin one. I like the one that's 6 3/4 inches. Oh yeah, but that's a low static unit. The high static are going to be like, 9, 10, 12 inches. So if you're going to do this sort of thing, that's got to be a high static unit. There's just no question about it. You're messing with disaster. You start trying to duct this thing. That's probably why they're making them, getting rid of them, because probably too many people do that. Okay, ceiling cassettes, who knows? Maybe that might fly. Certainly in your office. Wall mount consoles. Side discharge condensers as opposed to vertical stuff. They do have some drawbacks. The discharge of this, well, if you got nothing in the way over here, that's great. And you're sort of blowing the air and the noise away from your house. If that was this type of unit, then maybe it gets in the soffit. You got other issues where you can have, the weather is, the prop fan there is exposed to the weather and so forth, and leaves and whatever else. This guy's a little more protected. In fact, you can probably snuggle them under the eave here. Again, you can do whatever you want. Cover the top of them, put little blocks under them, get them above the snow line, wall mount them. Nothing wrong with doing any of this. Just want to make sure you keep your bends to a minimum, unrestricted airflow around the unit, distances to obstructions, I'm talking about in front of it. Access, you got to be able to get to it, so hopefully this thing comes off. Keep it out of the sun, I guess, or in the sun in winter. You don't want to put it next to the ocean. That's probably not a good move. Windy spots, not good either. These are all pretty obvious things that I'm sure you guys know already. Condensation, that's a big one. Basically in a side yard, don't locate it in a side yard. If City of Vancouver, just forget it. It's not even on the table. So is it going to be in Coquitlam or Burnaby? Or if it is now, probably won't be as soon as a few people start complaining. So why don't you just forget the side yard. Unless, of course, it's, the side yard you've got, the next house is way the hell over there and you think it's not going to bother them and the municipality agrees with it. Maybe that's the better way to go. But I would just not do that if you can avoid it. Yeah, I don't want to put them in a garage, maybe a parking garage if you live in a condo. Sunken patio. So let's say it's, Vancouver house, and you got yourself a walkout sort of basement, made a little patio there, and you got 8-foot walls, and you walk up the stairs, and there's the backyard, and you probably got a suite over the garage or something. Well, there's your patio. Hey, is that a good place to put it? Let's say we're a heat pump in cooling mode. Great. So we got that air coming through that heat exchanger, and it's in cooling mode, so we're rejecting heat. You can feel that. It's nice warm air coming on. Ah, that's nice. It rises up, and it goes above the patio and off into space. But now it's January, and that thing's been pulling heat out of air, and what happens? You get a nice little pool of cold air. And what's the poor heat pump having to deal with this whole time? You get this cool air pooling. You're hoping to bring in some warmer air, but you're filling that patio space with nice cold air. The thing's going to frost up because the air is so cold. It's going to frost up. Now, okay, well, let's go on defrost. Okay, and it's a nice patio out there. And now all that water drips down, and maybe, forgot to put the drains over there. And on its way to the drain, because that environment is now so cold, it freezes on the way there. And now what you've got is a skating rink for the kids. So it's just really not an efficient way to go. So be very careful, especially if it's a smaller space. In heating mode, if it's for cooling, it's not a big deal. For heating, though, you're going to chill that space. It's amazing. I've seen it happen. Learned it the hard way, in fact. Make sure that that thing, when it does defrost and you've got that liquid and it's going to freeze and it's on the sidewalk, you've got to have some drainage there. Somebody will get hurt eventually. So, I mean, sure, if the street there, now use up the side yard. If it does not affect the access path. And so there's a particular place, even if it's over here, it's got to be 5 feet, basically, from that property line. So you adhere to this, and now you need a mechanical permit. If you're going to do this, the electrician needs a permit to hook up a heat pump, and there's certain regulations for him, and then we need a permit. And we have to show them on this drawing, you know, a site plan like this, you've got to show them where the thing's going, the capacity of the unit, and a heat loss. You've got to provide a heat loss and some level of design. So, and they're advising below 55 decibels. It refers to it as a suggestion more so than a hard law, I think. But that's kind of tough to do. I mean, 55 decibels. This is a front yard. That's a kind of a crappy situation. It looks not great, but at the end of the day, what's wrong with it? It's hidden from view, in their opinion, and it's got good airflow. Nothing's obstructing it here, at least 5 feet there. It's out of the weather. Same thing here, under decks. You don't have to get real fancy. It doesn't have to be perfect. But what you don't want to do is start putting obstructions in front of that. That's just not good for the airflow. I think we all know that. But don't even try it. Don't even try it, even though the homeowner says, oh, look, it's open in front of the stairs. Well, no, it's not. It's open here and here, but what about this big obstruction here? The fan motor is not going to survive very long. Dryer vents, that's awesome. Awesome right there. So if these are back to back right now, so your airflow is actually this way and that way. So if you were to try to turn it the other way, I mean, I guess it's pretty obvious. If you flip this around and this one discharges into that one, this guy's going to have, well, probably still a crappy life because he doesn't have 5 feet here. But this guy's going to have an even worse life because this air has already been robbed of all its heat before it goes into this one. So in this application, that's kind of a bare minimum, but back to back, okay. Just don't ever try to discharge one into another. Yeah, just pay attention to the clearance requirements. They're in the manuals. All kinds of different ways to support them. We like these things, use a fair amount of these. I don't know, this is just something, you can make whatever you want, get it off the ground if you're in an area where there's a lot of snow. This stuff sort of seal up your penetrations, and they're gonna get more and more, the envelope guys and energy advisor, everybody's looking at this stuff now. So it's a good idea to use this sort of thing, seal as much as you can. You can buy these little kits to hook up your heat pumps and disconnects and so forth. Defrost mode, well, there you go. We had this conversation. I'm saying this guy's got other issues. That's well beyond when you should be defrosting. But that's the idea. And of course, all of that moisture, when it comes off of there, it's got to go somewhere. I mean, this guy in his lawn or wherever this is, probably be fine if it ever works again. But you really got to pay attention to where that condensate's going. We're going to have so many of these heat pumps, there's going to be a lot of condensation everywhere. Heating capacity, coefficient of performance, heating seasonal performance factor, capacity, rated heating capacity, and of course, AHRI is what we're looking at really for everything. Coefficient of performance, heating delivered divided by the electrical input. We can compare it to the efficiency of gas-fired stuff in a sense, not really. Heating season performance factor, that's your yearly energy use, where we're going to look at the defrost cycle in there as well. Heat pump sizing, well, that's a pretty important part. Must be identified by the outdoor design condition for the location where it's installed. Obviously, if you're going to have a different design if you're in Prince George than you're going to have here in the Lower Mainland. If you look at the AHRI and really all manufacturers, you guys are pretty much all using 47F and 17F. Coincidentally, we're pretty close to that with our design temperature. Kind of makes it easy, thanks that everything's in the data. This is the other thing that makes heat pumps in the Lower Mainland, Vancouver Island, the ideal application for a heat pump is the simple fact that we are at, on average, if you had to clock the outdoor temperature, 47F. So it really is in the sweet spot of a heat pump in the Lower Mainland, Vancouver Island. Of course, the first thing you do in sizing is to understand what your heat loss is. There is no question, and this has been for some time now, CSA F280 format. That's it. That's all there is to it. You got to do it. That's the only one. There is no other format for heat loss calculations. Like it or not, if you're doing a retrofit, you could probably just do a block load. Add up your glass, add up your structure. You don't have to do room by room. If you're not changing these rooms, then why would you do it? Maybe you do it anyway. Maybe you like doing heat losses. I've yet to meet anybody that's like that, but there you go. And it's obviously in new construction, it's going to be room by room. That's the first step. Find out what your heat loss is. Balance point definition. The point where a heating capacity curve of the heat pump intersects the building's heat loss line is called thermal balance point. So basically at that point, your heat pump is running 100% of the time. At that thermal balance point, that's the most it can do, and that's where the heat loss is. It's running 100% of the time. If it's beyond that point, then we're into something else. So in this case, here's our heat pump output. Of course, it's going this way. It's dropping as our outdoor temperature drops, and where the heat loss of the house heating requirement, where they meet, that's our thermal balance point right there. So that's, everything else is diminishing returns as we run our heat pump. That's our range. This section here is, you guessed it, it's supplemental heating. Now that's not such a big deal necessarily, is it? In this case, here's our design outdoor temperature. So our heat pump output is actually well above the outdoor design temperature. This is where we come up with this little area here of supplemental heat. Not the end of the world. You just have to size for it. When it comes to this, you can provide supplemental heat. Who would say, well, maybe what I'll do is, what if the thing breaks? So if I got to put elements in there anyway, maybe I just put in elements that can take over for the heat pump completely. 20 kilowatts or whatever you might be able to stuff in that heat pump. Who would choose that? So let's call that backup. Where the heat pump dies, I don't care, I got 100% backup. Or who would choose to say, well, no, I just want to provide kilowatts from here to there. Maybe it's 5 kilowatts. What would you guys choose? The backup, 100%, or would you go with a supplemental heat? So you're already taxing the whole entire panel just by putting the heat pump in. Now you're going to put in 20 kilowatts on top of that? Moving forward, I don't see that as being that viable. If it's gas-fired and you got the dual system, but when it comes to kilowatts, we're probably working in this zone here, just using supplemental kilowatts. Certified energy auditors. They're pretty much doing calculations on all new drawings these days, and most retrofits, particularly if you want the Greener Homes grant, you have to have the certified energy auditor come in, and he goes in, and what does he do? He looks at the house in the form of analyzing yearly energy usage and what sort of GHGs are associated with that. That's his job. He's checking boxes to make that all, figure that all out. And it's not, he doesn't care about heating, he does, but insulation, air leakage, roof, blah, 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 glass. These are the things that go into his Hot 2000 program. So, and you might say, well, dude there, he's already done it. Everywhere I go, he's already done the calculation. But a lot of them don't even include the peak load. They might know it, but they don't even, it's because they don't care. They care about the year. They don't care about the moment. They want to know how much energy you're using over time. So you can ask them for it. They go, oh yeah, I got whatever the peak load is. Is that good? Not really. It helps in the sense that you could use it as a reference. And those guys do check a lot of boxes, of course, but they will have good input on, because they're analyzing, that's their job. They're analyzing insulations and everything, insulation and everything else. What I hear now from certified energy guys is that the contractors are oversizing things. We're still old school. Maybe it's because the furnaces are only so small. We got to be that exact. I mean, we both have to do the right thing. We can't just, just throw in glazing and air changes and stuff. These things make a big difference. And so it's worth it to look at the result of the CEA's results to compare to yours. Maybe even just look at the insulation factors that you use. A lot of that information they already have. So use it. But you can't use it. At the end of the day, you have to do it. You got to do your own heat loss. That's all there is to it. And you guys have the disclaimer right on there that says, thou shalt not use it. And why is that? Because you don't want to get sued. Because that would be the best thing in the world. Well, he said it would work. He said it was 40,000. That's what I put in. And now you have the liability. So it clearly states, don't use this number. But it helps to work together. Electrical stuff, well, we all know that, we're 25 to 40 amps easily, if not more or less. We're all over the place, and there's tons of panels out there. If you're in the retrofit business, there's hundreds of thousands of, 100 amp panels. So you got to get pretty creative. So if you got a panel, I can't afford to do the upgrade. I know there's $500 or whatever to replace my panel and put in upgrade to 200 amps, but it's still thousands of dollars. I got to change my landscape and put in a pole or whatever you got to do. It's a big pain. I don't really want to do it, so that could crush the whole thing right there. Well, now you got to be creative. One thing I've been looking at lately is dryers. You're taking the gas line off the furnace. You're capping that rascal anyway, and the laundry room's right there. How much is a gas dryer? Get rid of that 18-year-old electric dryer. There's 30 amps right there. Slide in a gas dryer. Maybe that's the solution. I'm just saying you can be creative, work at it a little bit. So I know you don't want to talk about rebates, or maybe you do. So if you take the way the rebates are now, and I just use an example of, if you got yourself a tier 1 system, and you look at what's available there, you got Clean BC, $3,000, BC Hydro, $3,000, City of Vancouver, $6,000. Jesus, that's not bad. Victoria, these guys, North Van, $2,000. District, North and West, $2,000. That's $12,000 right there, just with these two. And then you go, oh, we got the greener homes thing. We put in the nice greener homes thing with, now they want an HSPF of 10 or more, so it's automatically fairly expensive equipment. Does it justify the extra $4,000 to $5,000? I don't know, maybe it does. But that's $17,000 right there. That's a lot of dough, really. So you can see why people are focusing on this and saying, well, why don't I do this? And honestly, I don't have an argument for that. Your furnace is 18 years old. It could crap out any time. You need a new one. These guys are going to give you $17,000, put in a heat pump, and you got air conditioning. Seems like a fairly straight ahead thing. Now, that's not for everybody. Obviously, the hybrid stuff is less. Well, hybrid's not going to qualify in Vancouver. But wherever that might happen, obviously there's diminishing returns as far as rebates go. So this would be like a home run sort of thing. Is it a headache? Well, the homeowner does this part. And the certified energy advisor does this part. So we're not doing that much. But what we are doing is we go, oh, okay, great. So I got to do this heat loss thing. I know that. So I do the heat loss. I figure it out, or at least I'm just pricing it now. So I got to figure out what it's going to take. That's a big headache, isn't it? You say, well, you know what, I'm ballparking right now, but this is probably a 4-ton unit. I got to analyze the ductwork, measure, and I got to look at, make sure the static and everything else is good. There's a fair amount of time involved already. Think about, okay, I think I've got just the one. Oh yeah, I better look up and see, is it on the greener homes thing? Oh, it's not on there. Oh, but it is on the Clean BC. Well, we could get 6,000. Well, what if I switch? Well, what's on the greener homes one? You look at the greener homes one. Now it's been 3 hours already. You haven't sold or done anything. You haven't done anything. And And so now you finally get it fair. Finally, I looked at all the grants, the available equipment, everything else, call up the wholesaler. Hey, have you got a blah, blah, blah 4-ton? Well, let me see. I got the condenser, but I don't have an air handler. Well, how long for one of those? It looks like 4.5 months. Okay, how about, do you have a 5-ton? No, I don't have the ductwork. Well, I could go down, I could add an element. Okay, do you have one of these? Oh, yeah, I have one of those, but you check back there, oh, it's not a rated appliance. It's not going to get the rebate. You can spend a whole day and you haven't really achieved anything for anybody. So at the end of the day, how do you factor all this in the price, in the cost of it? I think you have to. I think you have to factor in this extra amount of work. I mean, I've been doing this for a long time, and our work now is really quite technical. In a way, I kind of like it. I kind of like it that they're forcing you to do all this stuff. And so now this is everybody's over an HSPF of 10 as of October 30th. So it forces you to do a lot of research and a lot of analysis. You've got to look at the performance of that heat pump, make sure it's going to heat the place. You've got to find the equipment. In a way, it does force you to get right into the nitty-gritty of things. It's not like 20 years, you're going to take the 80,000 BTU furnace and throw it in.